Okay, welcome back. This is the first video where we're going to practice doing some calculations with a heterogeneous equilibrium, and it follows in the playlist from the video where I defined heterogeneous equilibria. So here's what the problem is, and we're going to in this problem we're going to combine a large number of concepts that we've already learned about. So there's going to be a lot of stuff that we're going to do in this particular video, starting with dealing with the fact that this is a heterogeneous equilibria. So let's look at the problem at hand, at least initially. So we've got 10 grams of ammonium hydrogen sulfide that's combined with 0.23 molar ammonia and 0.23 molar hydrogen sulfide. And these amounts are combined together in a 1 liter flask at some fixed temperature. And the initial question is, does more ammonium hydrogen sulfide form in the reaction? Now, this combines a lot of different concepts. The first being that we need to utilize the idea of the reaction quotient to figure out which direction equilibrium is going to shift, because we are combining initial amounts of these components. These are not equilibrium amounts. So the first thing I'm going to do down here on the right is I'm going to write the equilibrium expression for this. And since we're in molarity, we're going to write a Kc. And the Kc is going to be concentration of NH3 times concentration of H2S. Remembering that since this is a heterogeneous equilibrium, the ammonium hydrogen sulfide, the NH4HS, is not included in the expression. And the value, Kc, is equal to 8.5 times 10 to the minus 3, which, by the way, is a small equilibrium constant. So the first thing we're going to do is we're going to calculate a Q value so we can figure out which way equilibrium is going to shift. So all we're going to do with this is input the concentrations of the relevant initial concentrations of the relevant species. So we've got 0.23 molar of the ammonia, and we have 0.23 molar of the H2S. And when we multiply those two values together, remember, so there's another learning issue here. The Kc and the Q are written the same way. The Q only has initial concentrations in it, and since this is heterogeneous, the 10 grams of the NH4HS doesn't matter here. So the Q value that I get is actually 0.0529, which is the same as saying essentially 5.3 times 10 to the minus 2. So in this case, it's super important to realize that Q is greater than K. And if Q is greater than K, what that means is that our initial concentration of products, so this is non-equilibrium, so initial, I'm just going to abbreviate it like that, is greater than the concentration of products that should exist at equilibrium. And I'll write it this way. So what that means is that the reaction must shift left to get to equilibrium. So the answer, the short answer here is yes. More NH4HS is going to form. Now what I want to do to extend this problem is actually calculate the equilibrium concentrations of NH3 and H2S and determine how much NH4HS is actually going to form. All right, so what we'll do next is we'll set up our ICE table, or in my classroom I call it the box. So before any reaction, we've got 10 grams of this material here. We've got 0.23 molar of the NH3, and we've got 0.23 molar of the H2S. Now, the 10 grams of the NH4HS doesn't matter because as long as there's some solid present in the reaction container, then the individual density of this material never changes. No matter how much new material we add to it, the density of the solid remains the same no matter what. Now, after we reach equilibrium, we're going to have 10 grams. This really should be represented as molarity, all right? I'll put a parenthesis around it. I'm going to put this here at more or less as a space holder. And we're going to be gaining material here, and we'll be gaining by x. It's x because my coefficient in this is 1, and the coefficient for the ammonia is 1, and the coefficient for the H2S is 1. And these guys each are going to decrease by x. And we're in molarity. I think I defined, yes I did, I defined our reaction vessel as being in 1 liter. So actually the 0.23 molar is also moles, but you know, let's just keep moving with this. All right, so now what I'm going to do is set up my Kc expression. So it's going to be 0.23 minus x, and I'll go ahead and just show that as quantity squared, since we're going to be multiplying this value times this value, and the two quantities are the same. So this is going to equal 8.5 times 10 to the minus 3. Now, this is a nice problem because literally we can go ahead and take the square root of both sides, so that we're not going to have to deal with a quadratic equation. And what we're going to get after we take the square root of both sides is going to be, on this side we'll have 0.23 minus x, and that's going to be equal to 0.0922. All right, now solving, we're going to have x is equal to 0.23 minus 0.0922. And what I get for my x value is going to be 0.1378 molar. All right, that's my x value. So now there's two things that I want to do to finish the video. The first is that we'll go ahead and we'll calculate how many more grams of the solid actually got formed in here. And since we're in 1 liter for total volume, the molarity, the additional molarity of the NH4HS that we're going to produce here is going to be times 1 liter. So this number times 1 liter. So we're going to form an additional 0.1378 moles of the NH4HS. Now, we need the molar mass of the NH4S in order to get to grams. So the N is, its molar mass is 14.01. There's 5 hydrogens for 1.008 per hydrogen atom. And then the sulfur is 32.06 for a grand total of 51.11 grams per mole. So to find the additional mass of NH4HS that's going to form, we're going to take the 0.1378 moles and we'll multiply by 51.11 grams per mole, and we get a grand total of about 7.04 grams. Whoops. 7.04 grams of the NH4HS that's going to form. All right, now let's go to the next part. I want to know the equilibrium concentrations of the final concentrations of the NH3 and the H2S. So coming up here, we're going to take and we will subtract from the 0.23, 0.1378. So what we're going to get for the NH3 and the H2S is going to be 0.0922 molar. Let's fix that up a little bit. All right, now, and that's going to be for each one of these at equilibrium. Now, we can double check right now to be certain that the way I set this problem up, whether or not all of this was done correctly. So what I'm going to do is I'm going to recalculate my Kc using the equilibrium concentrations that we just calculated for the ammonia and for the H2S. So that's going to be 0.0922, and it will be quantity squared since the equilibrium constant is the product of both values. When we do that, let me just run that number quick. We get 0.0085, literally. So this is 8.5 times 10 to the minus 3. And this value right here matches very well with the starting equilibrium Kc value that we were given. All right, so this example was designed to draw in several concept areas. The first being a heterogeneous equilibrium, where the K expression only includes the things that are not solids and liquids. We had to find a Q value so we could determine which way the reaction was going to shift to reach equilibrium, because we were given we were given initial quantities of the relevant components, and then we used the knowledge on which way the equation was going to shift to set up our ICE, and then we solved for the equilibrium concentrations of the components in the reaction, and we also found the mass of new solid formed. All right, and with that, I'm going to go ahead and close this video.